Okay, everybody? Week 10, we've made it. Is everyone excited? It's nearly the end. So we are going to talk this week about arguably one of the most important scientific and global issues that is going to face your generation. I used to say our generation, but I'm getting old. And so this is super important. I always say to people, even if you forget everything else that you learned in the other 9 weeks of this class, I really hope that you take something from this week. This isn't so important, it's not just that it's going to come up on the final and then you can forget it. You are going to be living here in this world. We're not going to be going to any other planets anytime soon. You're living here and you will be living here for the next decades. And there is going to be very profound change on the Earth over your lifetime. And the amount of change that we experience is going to be in some way controlled by you, controlled by the decisions that we make as a civilization. And so we've seen the start of that this week. It's very good timing for our discussion on Thursday. We saw that the Obama administration and the Environmental Protection Agency just yesterday announced for the first time that we're going to be imposing limitations on the carbon emissions from power stations, in particular coal-powered power stations, which are some of the worst polluters. And so we'll talk much more about this on Thursday. But today we're really going to look at sort of how Earth's climate has been changing just over the last 100 years and what we can sort of learn about that. Why is it changing? How certain are we about that? So, some admin to get us started. Extra credit. Any remaining extra credit that you would like to submit is due by Sunday at midnight. There are drop boxes on the EEE website that you can find to upload your assignments if you would like to do that. One reminder, please don't upload your assignment in Pages format for those of you with Macs, because I'm not yet in the Mac world and so I can't open those. So please make sure you either save it as a PDF or as a Word document. Regrades, if you think that we've unfairly done you out of points that you deserve, please do bring that to our attention before the final. There won't be any regrades after the final. So if you have discussions or your midterm that you would like us to take a look at and explain why you lost points, then please do see me or the TAs before the final. Does anyone have questions about that? No? Okay. The final. It is approaching, I'm afraid. It is not something we can ignore. It will be next Thursday, the 12th of June, and it's from 1:30 to 3:30, so note the earlier time. Please don't show up at 2. And it's going to be in this room. It's the same format as the midterm. For the amount of time that you have, it will be shorter than the midterm, and so there should be a little bit more time for you to look at, but it'll still be relatively long. I want you to show me what you know, and that's not really fair if I ask you 10 multiple choice questions and that's it. There will be assigned seating. If you didn't get a left-handed seat last time and you are left-handed and would like one, please do let me know so I can put you in one of those seats, and then someone who's right-handed doesn't have to sit in those. Things that you will need, the same Scantron form as before, student photo ID, pen and pencil. Instead of a note card, you can now bring a full page of notes, but one-sided only, please, okay? And that would be handed in, again, as normal. The study guide is available on the website, and you can find answers to the midterm as well as all of the answers for your quizzes so far in EEE. So do make sure that you take a look through those and try and learn from where you lost points as you went through the quarter. I'll be available in my office on Thursday that morning if you have any panicked last-minute questions, which hopefully you won't, but just in case. And there will also be a final review session, and I'm sorry that it's so late, but that's the only time we could get a large room. So it will be from 7 to 8 p.m. on Tuesday the 10th, okay? And bring your questions for the TAs for that. Does anyone have questions about the final? Not yet? Okay. So, in that case, let us make a start by looking at our quiz from this weekend. So mainly this was a great quiz. I don't think there were very many things that people missed. the one that stands out is this question at the top, which is one suggestion for reducing the heat island effect is to create these green rooftops. So this funny idea that our cities might end up looking more like this in the future. And so how would that reduce the heat island effect? So a lot of people put that we'd increase the sensible heat to latent heat ratio. And actually that's one of the causes of the heat island effect, right? And that's because in the urban areas we've paved over a lot of the sort of soil and vegetated areas. And so if you imagine that the same amount of energy comes in and strikes the concrete, and a similar amount of energy comes in and strikes, say, grassland, then all of that energy that hits the concrete and is absorbed is going to go into increasing the temperature. That's our sensible heat flux. But if we take a look at the grassland, instead, the same amount of energy coming in, more of that energy will go into evaporating water. And evaporating that water doesn't change the temperature necessarily, it just changes it from liquid to gas, okay? And so that's stored energy, it's latent heat energy, it doesn't increase the temperature of the surface. So what we're going to do, if we replace a lot of our concrete roofs with green roofs, we're now saying that there'll now be water in that vegetation, water in the soil that it's living on, which can evaporate. And so we'd actually do the reverse of that, which we would increase the amount of latent heat flux that's happening compared to sensible heat flux. So we would decrease the temperatures that we see. Does that make more sense now for the people that got caught out? Yeah? Okay. And then the other ones I think were really more or less perfect. So it's always nice and clear in LA after rain that water carries out particles. Sulfuric acid is a secondary pollutant because it reacts with water to form a new pollutant in the atmosphere. All of those others are directly emitted from the surface or from us. The low pressure belt, where we have low pressure, remember, we have air rising, and where we have air rising, we tend to have clouds and rainfall. More or less everyone got the idea behind the carbon dioxide concentrations and saw that just last month we hit 400 parts per million, which is quite an important landmark for us. I think most people got that the eccentricity cycle is C, okay? It's that cycle that shows the Earth's orbit getting from more round to more elliptical and back again. All of these different ways would help you reconstruct temperature, and I think these others are also fine. So well done for those of you who took the quiz. I thought that was pretty good this week. So we are going to do 3 main things today. The first is going to be very quick, because it's really just a review of what we did last Thursday when we started talking about the climate system and talking about the ways that we reconstruct it and what we've learned from that past climate. And then we're going to look at 2 main ideas. Okay? The first is, how has our climate been changing? So what evidence is there? What aspects of our climate system are changing? And then second, or the third question, the last thing we'll do today, and spend quite a long time on that, is why is our climate changing? What have we learned about why we are seeing what we are seeing, and what does that mean for looking into the future? Okay, and this sets the stage for what we're going to talk about on Thursday, which is, what is our future going to hold? A lot of that is really up to us right now. Okay, so first of all, a reminder, this is the climate system. And the reason that we get so tangled up when we talk about the climate system is because it's such a complicated interlacing of lots of different things. So we have our geosphere affecting things like volcanic activity, which influences the atmosphere. We have our oceans, and the movement of that water influences both local temperatures, but also the larger global pattern of, say, atmospheric composition and energy transfer. We have the biosphere, which obviously has had a huge influence on the composition of our atmosphere, but also it affects things like albedo of the Earth's surface. So all of these things we have to take into account if we're going to talk about how our climate is changing and start thinking about why. Can we tease apart all of these different things and put our finger on one thing and say, that is why our climate is changing, okay? And so from our past climate, I showed you that we have these really amazing sets of records from different proxies that give us information about the past. And there are three things that I would like you to be aware that we have learned about this current situation from our past climate. And that is, yes, the world has absolutely been warmer in the past. It's also been a lot colder in the past, okay? The world isn't going to suddenly end because our climate gets a few degrees warmer, okay? But the world at those times was very different. The conditions that we were experiencing was very different. And if we look at human civilization and current life on Earth, it is very much adapted to our current temperatures, precipitation patterns, and everything else. And it's used to being very stable. We remember we looked at the last ice age, the last glacial period, and we had these big swings in temperature. That's not something that we've experienced in the history of human civilization on Earth. And so if we see this very dramatic change, that's going to really take us out of any situation that we've been in before. And in particular, if we want to look at the rate of climate change that we might see in the next 100 years, that rate, if we look back over at least the last 65 million years, is really unprecedented. And it's the rate of the change, the speed that our climate is changing, that really can cause the most damage. Because with an increased speed of climate change, it's much, much more difficult for us to adapt to it. It's much more difficult for natural ecosystems and life to adapt to that. And these are ideas that you're going to be doing in discussion this week, those of you who've made it. And this is a graph that you would see if you go to discussion this week, showing our reconstruction of carbon dioxide levels, given that we talk about that so much, for the last 65 million years or so. And so that all those dots represent different data points going back in time, and you can see we have less and less data. But you can see that right now, at 0, we have relatively low carbon dioxide concentrations compared to previous periods in the past. But if we're sort of looking at pushing up into these higher levels, then we're really pushing the Earth back into a state it hasn't been in for millions of years. And we're doing that in just 100 years. And so that's the real sort of message, that it's the speed of that change which is so dangerous. So, first eye clicker of the day. Let's see how people remember information from last week. So which of these images here shows a reason, does not show a reason that climate can change? So 3 of those show mechanisms that cause climate change. 1 of them doesn't, okay? So talk to your neighbors, see if you can work out which one represents something different. Okay, let's take a look and see how we did. Okay, so let's talk about what each of these are, and then I'll ask the question again. So what does my image A represent? What do you think that represents? Yeah, it represents a Milankovitch cycle. It represents the eccentricity cycle. Okay. What does B represent? Giant volcano, right? How could that change climate? More CO2. What else do you see going into the atmosphere? Aerosols, absolutely. What does C show you? Sunspots. What does D show you? The ozone hole, okay? So tell me, which of those is not a mechanism that causes climate change? Vote if you haven't had a chance to, and we'll see if we get a better spread this time around. Okay. So we still have a bit of disagreement, and this is a fundamental sort of misconception that people have. How would the ozone hole cause our climate to change? How could ozone, or the lack of ozone, cause our climate to change? So this is something that people really think about, and it's something that we can find in young kids and adults and everything else. People think that the ozone hole is behind climate change for some reason. It's a completely different problem. The lack of ozone doesn't really affect things like our greenhouse effect, Okay? Because remember, ozone doesn't really respond to that infrared energy, which is how the greenhouse gases are keeping that energy close to the ground. Okay? What that ozone does is it blocks incoming ultraviolet radiation. So the lack of ozone in our stratosphere means that we're not absorbing as much of that. If anything, it causes a very, very, very slight cooling. But it doesn't really affect our global climate system. Okay? Sunspots definitely do. We have our 11-year sunspot cycle, and that actually affects how much radiation is coming out from the sun. Okay? And so that really does affect our climate here on Earth. The ozone hole doesn't have an enormous influence on our climate. Okay? And that's something that everyone gets wrong every year. So I'm going to put it in the exam this time. Make a note. I'm going to ask you, does ozone control sort of greenhouse effect? You have to put no. Okay. So these are our 7 reasons. If you remember, we had these different reasons that we can identify for why climate will change, and that they really are tied into our understanding of what controls our global temperature, both ours and every other planet that we can see around the solar system. And that is variations in solar output. The more energy from the sun, the warmer we're going to get. The distribution of continents, mountains, oceans, that influences the movement of the atmosphere, the movement of the oceans. It also affects albedo to a certain extent. Surface characteristics, again, albedo and things like the exchange of moisture and energy across the surface. Changes in greenhouse gas concentrations definitely affect our climate because they trap more of that outgoing infrared radiation, and that can warm us up here at the surface. Aerosols are tricky because depending on what they are, depending on where they are, they can both act to reflect incoming light and so cool us down, or absorb outgoing radiation, in which case they warm us up. Okay? And then we have changes in Earth's orbit, our Milankovitch cycles, and we have these feedback processes going on. So these are our sort of mechanisms of change. And we'll come back to thinking about these when we talk about why our climate is currently changing today. Okay, so let's take a look at some of the pieces of evidence that shows that our climate is changing. And people were mostly with me last week when I asked this question, is our climate changing? It is definitely changing. But I know that a number of you who gave me your questions had specific questions about things like ice in the Arctic and elsewhere. So I've tried to answer as many of those as possible as we go through. But first, I want to introduce you to the most important documents in our sort of thinking about climate change. And this is the Intergovernmental Panel on Climate Change. And we're going to call it the IPCC for short, because I can't pronounce that every time. And if you ever have to do a little writing project or research project or anything to do with climate change, this should be the first place you go. There is an awful lot of complete nonsense on the internet. I know you know this, but it can be difficult to identify whether something is nonsense or not. Okay? This is definitely not nonsense. Anything that goes into the documents that are produced by this organization has to be peer-reviewed. If I want to produce something scientific, or the TAs want to publish a scientific paper, we go through what we call peer review. We write up our paper, we say what we did, we say what we think we had learned from it, and we send it to a publisher. They send it to other scientists who anonymously review what we've done, and usually tell us in no uncertain terms what we should have done and how to do it better. And then it comes back to us and we try and fix that, or we address those comments. And if it's acceptable, then it ends up being published. Okay? So it's a long process and it has to be approved by other people. And anything that goes in here has to be peer reviewed. Okay? And this in itself is peer reviewed. Okay? There are 120 participating countries. And for the little summary of each of these reports, every single one of those 120 countries has to agree every single word. And you can imagine what a challenge that is in terms of a scientific sort of document that then gets used in a political way. And so various countries want certain terms taken out, certain things added in, and then it's a big giant fight. It's basically a war of attrition until we get to something final. And so really this is the place to go, okay? And I brought you not the most recent one, which was published this year, but some from 2001. And this is my challenge. I have to fit into this lecture, last lecture, and the lecture on Thursday, everything from this. And I'm not, okay? And so if you want to find out more information, this is the place to go. We have the science. We have the impacts, adaptation, and mitigation, basically how we can prevent the worst of that hazard, or vulnerability rather. And then we have a whole book on mitigation, how we can prevent it happening or adapt to it in the first place, okay? So there is enormous amounts of information, and this is from 2001. They get thicker every year. We stop buying them after that, okay? And so it's really the first place that you should go, and it's really pretty conservative. And it's very exciting. Hopefully you saw some of the press about this earlier this year. And I want to make the point that this is not really a scientific issue anymore. There is a certain, it is a scientific issue, but really the science behind what we've been saying hasn't changed a lot, okay? And so really, I want you to think about where your interests fit in, because right now we need politicians, we need economists, we need psychologists, and we need engineers and other people who can sort of help us deal with communicating this information, adapting to the changes that we're seeing and that we will see in the future. And so think about that as we continue. This report also is very careful about giving a range of uncertainty. And I haven't listed all of those today, but there are certain things that we know with great confidence, and there are certain things that we are a little bit shaky about, okay? But there's an awful lot now that we are getting really quite certain about. And in terms of scientific certainty, we are never 100% certain about anything. We are not 100% certain that smoking causes cancer or anything like that, okay? So if we're talking about probabilities of 99% or 95%, that's really pretty amazing given how complex our climate system is, okay? So we do have these assessments of uncertainty, and you might well see that if you dive into the report. So, why is our climate changing, or how is our climate changing? Both are tied into this same graph, okay? So this is an update of that Keeling curve that you've seen a couple of times now. Now it goes up to 2013, and if we included it up to this month, it would have broken through that 400 parts per million line there, okay? And we haven't had that sort of CO2 concentration for at least a couple of million years, most likely, okay? So our carbon dioxide levels in the atmosphere are increasing. If we look at our atmospheric temperatures have been increasing. We've seen a warming of 0.86 degrees Celsius from 1880 to 2012, which is sort of the last data point on this, okay? It's likely hotter today than it has been at any time in the last 1,300 years, and that's really sort of where our uncertainties increase going back in time. We have also seen increases in the frequency of heat waves in Europe, Australia, especially in Asia. Okay. And so what you may have heard about in the news more recently is the pause in global warming. Has anyone heard of that? No? Okay. Well, there's an awful lot of debate about what seems to have been this little plateau. A lot of people will look at this and say, oh, it's stopped. It's all right, global warming has stopped. Okay? That isn't true. If you look at the decade averages, it's still going up. There's no reason why it's not going to continue going up. There is a certain amount of noise in our climate system, and you can see that. You can see that for this period of time, if you just looked at that period of 20 years or so, it would be decreasing in temperature. But overall, the trend is increasing, and there's no reason to suspect that is going to change. So here is a map showing that temperature increase, because that temperature rise of 0.86 degrees Celsius isn't the same everywhere. Some places have warmed more than others. So where has the greatest warming been, do you think? Over the oceans at the equator, over the land at higher latitudes, or over Antarctica? So take a look at my map, take a look at the scale underneath. and work out where has the greatest warming been so far in just the last 120 years. So 80% of people agree with me that really the biggest warming is really those purple colors. And where are those purple colors? They're really over the land, not over the oceans. And they also seem to be towards the poles. Okay? What's happened to temperature over Antarctica? Has nothing happened to temperature over Antarctica? Is there any white on my scale bar? No. So what do you think the white areas mean? We don't know. And why might we not know? It's an obvious answer to this one. Sorry? It's hard to measure, yeah. But we don't have measurements. Because if we look at those white areas, they're in the middle of the oceans, they're the Antarctic, they're areas where there aren't a lot of people. They're areas where we probably don't have measurements from 1860, 1870, 1880. And so where we're uncertain, where we don't know, we won't include that on our map, okay? But really, if we look at where the largest temperature changes are, they really are in our sort of Arctic areas, especially over land at high latitudes. Okay. If we look at our oceans, unsurprisingly, if our atmosphere is warming up, our oceans are also warming up, and they are warming up much more slowly. And that makes sense, right? Because if you put a pan of sort of pasta or rice or something on the heat, it takes a really long time for that water to heat up. It has that high specific heat. And so this is a really significant change in ocean temperature over this time. There's an enormous, enormous amount of energy going into our oceans, okay? So here's our ocean temperatures. I unfortunately cut the time scale off the bottom axis, but you can see that through time there's been an increase, and as our data gets better, we have a better idea of how much temperature there is. And if we look at the most recent sort of decade or so, when we see that flattening of the air temperatures, we don't see as much of an increase as we were seeing before. What we have seen is that we're seeing much more energy, much more of that heat energy actually going into our oceans, okay, in the last few years, which explains why our atmosphere hasn't been going up as much. And really, the fact that our oceans are there and have this really high specific heat capacity and are really sort of taking in an enormous amount of energy is really saving us from much more extreme temperature rises in our atmosphere. Okay? If we look at how much of the extra energy that we're getting on Earth has been stored in our ocean, we have something like 90%. Okay? So imagine if all of that had remained in the atmosphere, we'd see much, much higher temperature changes than we have been doing. Most of that energy has really been going into warming up our oceans. And so we've also been seeing an increase in sea level at the same time. Okay? If we look over the last, say, 100 years or so, back to 1900, we've seen maybe a 20 centimeter change, something like that, in sea level, which is not inconsiderate. It's quite a bit, okay? So what is the main reason that our sea level has risen over the last 100 years? So tell me, is it the melting of Greenland? Is it the melting of glaciers up in our mountains? Is it that the ocean is warming up, or is it that there's more rainfall over the ocean? So tell me. And any of you from oceanography should definitely not get this wrong. I'll hunt you down if you do. So let's take a look and see what you think. So the majority think A, the second majority think B, and anyone who took oceanography with me last quarter put C. Because actually, the answer is C, okay? And this is another one that catches people out, okay? So as the ocean warms up, what do we know happens to warmer air? It's less dense, it expands a little bit. As our ocean warms up, it expands a little bit. And if you imagine warming up 4 kilometers depth of ocean, that expansion adds up. And so we've actually seen an increase in sea level, not necessarily just because we've been adding water, which we certainly have been, but actually most of that rise is just because the oceans are warming up. Isn't that fun? So, yes, over 50% of that rise that we're seeing each year is just because the oceans have been warming. That doesn't mean that we're not adding even more to our oceans by melting both Greenland and Antarctica now, and also these mountain glaciers. And definitely as we go into the future, as we're seeing really much more rapid melting of Greenland and Antarctica, those are the ones we're really concerned about. Because thermal expansion of the ocean, that sort of increase in volume of the oceans due to temperature rise, will certainly contribute a not insignificant amount to our sea level rise. But if we melt significant chunks of Greenland, if we melt significant chunks of Antarctica, we can add several meters of sea level rise. And that really does change what we start talking about. Okay. The other thing that doesn't ever get talked about, but is really extremely important, and we know with much better precision and much clearer answers than some of what we talk about in terms of temperature and precipitation, is that as we put extra CO2 in the atmosphere, more CO2 dissolves in the ocean. Okay? And if we get more carbon dioxide dissolved in the oceans become more acidic. Okay? Everyone knows that when you open the soda bottle, you get the bubbles and they're of carbon dioxide. It's carbonated drink, okay? And it's not good for your teeth because it's slightly acidic. Well, it's the same thing for the ocean. If we put more carbon dioxide into the ocean, that carbon dioxide reacts with water and it produces carbonic acid. It's a weak acid, but it's still an acid. And so you can see that even with just our measurements from 1990 to 2010, we've been dropping in terms of pH units. And remember that that's a log scale. The pH scale is a log scale. And so we've seen something like a 30% change recently in our pH. And in fact, if you look at the coast of Washington State, they are actually starting to see real effects of this, both due to pollution and the location where they are, which gets much deeper, more acidic water coming up. But they have seen failures in their oyster crops recently because their oysters make calcium carbonate shells, which dissolve in more acidic waters. And that's our concern, that as we increase the pH, or as we decrease the pH and increase the acidity of the oceans, then organisms that produce shells, things like corals, even things like fish that produce little calcium carbonate ear bones, could start to be very much affected. Unsurprisingly, as temperature has been warming, ice has been melting. I don't think that would be a stunning surprise to anybody. And so we can see that both snow cover and mountain glaciers have been melting. And you've seen the effect that that has on our water reserves here in California, but that's especially true of communities around the Andes, around the Himalayas, very populated countries that get a lot of their water from glacier melt, snow melt in those drier seasons. And if that isn't there, then they could be in trouble for their water supplies. We're seeing loss of ice from Greenland and Antarctica, increasing amounts of loss from those locations. And for those of you that were reading the news last week, we looked at West Antarctica, which is starting to melt underneath due to rising ocean temperatures. And really, if we look at that melt back now is more or less unstoppable. We've committed ourselves to a certain number of meters of sea level rise, and we'll talk more about that on Thursday. We've also seen sea ice decline. I have a couple of graphs to show you in a second. And also the area of permafrost has declined. Permafrost is something that you might not have heard of because you're all from South California, but permafrost is permanently frozen soil. So we get a lot of that up in, say, parts of Russia, parts of Canada and Alaska, where the soil is frozen. And so any sort of organic material, anything like leftover bits of plants and animals in that soil, don't decay. But now we're starting to thaw out that permafrost. It's starting to rise above 0 degrees Celsius, and all of that trapped plant and animal matter for the last few thousand years is starting to decay away. And that adds more carbon dioxide to the atmosphere, which worsens the amount of warming we're seeing. So it's another one of our potential feedbacks. Is everyone thoroughly depressed yet? Yes? Okay. So let's look at sea ice. Sea ice is changing amazingly quickly. We have about 50% less sea ice in the summers today than we had 40 years ago, 30, 40 years ago. 50% less. That's astounding. In your lifetime, it's entirely feasible that you will have ice-free conditions in the Arctic in the summer. That's going to be really very, very different. And no one ever hears about it. That's what drives me crazy. So here's sort of two maps showing that sort of the minimum sea ice extent in the September, which is at the end of the summer when there's been the most amount of melting, in 2012 at the top and 1984 at the base there. And you can see that there's really enormous change happening, and that change is also accelerating as far as we can tell. And if we look at our climate models, this sort of meltback is happening way faster than we thought it would, which is a concern for us. And so what do you think, who is interested in the Arctic Ocean? Who might be interested in this meltback of sea ice so that we can get to the Arctic? Oil, gas, absolutely. There's sort of quite nice oil and gas reserves off Russia here. If you remember a few years ago, they went and planted their flag on the seafloor. This is mine, okay? And so that's definitely something that definitely oil companies are interested in. Also, if you look at shipping routes, there's a nice shipping route now that you could go along rather than having to go around through the canals in Egypt and Panama as well, which is a really interesting opportunity for various shipping companies as well. So it's definitely an interesting change. In terms of the volume of the sea ice, so that showed you just the area. If we look at the area times the thickness of that sea ice, you can see that there has been an enormous decline in that volume as well. And as that ice gets thinner and thinner each year, it's much easier to melt it back completely in the summer, and that's why this process is accelerating, okay? How about precipitation? This is something that really affects us. And this is something that we don't have as good records of as we do the temperature, but we can certainly start to see some patterns. If we look at the sort of the most recent decades, you can see that the blue areas have been getting wetter, the brown areas have been getting drier, and the measurement is in millimeters per year per decade, okay? And you can see that tends to be wetter in Eastern, North and South America, in Northern Europe, and Northern Central Asia. But it's drier around the Sahel, which is that area around the Sahara in Africa, the Mediterranean, Australia, Southeast Asia. So in other words, we're getting dry places becoming drier, wet places becoming wetter, okay? And certainly what we're also seeing is that there's more extremes. We're seeing more floods, more drought, and those are getting more extreme through time, okay? And then lastly, I didn't want to skip past this without talking about the sort of changes that we're seeing in the biosphere, in the life on Earth. It's something that we think of as happening in the future, but there are already effects that we can see today. So for example, we're seeing earlier arrival of spring in some places. And if you look at organisms in an ecosystem, often there's quite clever timing involved in, say, when the baby birds hatch compared to when insects start appearing in the ecosystem. And as we start messing with the timing of, say, spring and the timing of snowmelt, for example, then we mess up those nice intricate timings, and so we see changes there. Rain shifts. So things are moving higher in elevation or towards the pole, and that's because they're sort of seeking the same temperatures. So we're starting to see forest systems moving northwards towards the pole, surviving in areas which they weren't doing before, okay? Food web disruption, we can see this in the Arctic. We had before, the base of our food chain, or the food web, was algae that used to live within the sea ice. But as that sea ice melts away, then that is replaced by other species. And so that has unexpected consequences sometimes within the larger food web itself. Something that affects us, for example, is expansion of parasites and disease into new areas. So there are various cities in Africa, there are various parts of Europe which were safe from malaria for a long time because they were just cold enough that mosquitoes wouldn't be able to survive and carry that disease. But unfortunately now, with a warming climate, the range of those mosquitoes has expanded, and now we're seeing those diseases getting to areas where they hadn't before. So that's also a concern for us. Who's heard of pine beetles? Nobody? No? Okay. Well, you should look them up because it's a really interesting and really sad phenomenon that's happening around in Canada and also coming down sort of through Washington State and Oregon as well, I think. I'm not sure if it's in California yet. But this is what a pine beetle infested forest looks like on the right-hand side there. And these pine beetles usually got killed off by really cold winters. And as if we've had milder and milder winters, then these things have survived and are sort of burrowing into trees and damaging them. And so their sort of range has expanded as well. Okay. And for anyone who is a plant enthusiast, I kill more or less anything I try and grow, so that's not me. But if there are any keen gardeners out here, there's a really cool little website here, if it will open for me. That shows the hardiness zone. So if you've ever gone to buy a plant, then we have these different zones, 3, 4, 5, 6, 7, 8, 9, 10. And what they tend to give you an idea is they're written on the label for the plant. And it gives you an idea of whether that plant is suitable to be in your area. So you wouldn't plant something from zone 3 down here in Southern California and expect it to survive. Okay? And you can see how these hardiness zones have been changing through time. So this was 1990. If we move forward to today, those zones have shifted. So for example, we used to be in zone 9 over here. Now we're zone 10. So you can see these things have been shifting northwards. And that's just in the last 25 years or so. So I think that's really interesting as well. Okay. So I'm not going to insult your intelligence by asking you this again, because really it's unequivocal. Our climate is changing. A lot of those changes are really unprecedented in terms of our records as far as back as we can look, in terms of hundreds, even thousands of years in many places. So our climate is changing. But why? This is the really fundamental point. This is what people care about. So if the climate is changing and it's nothing to do with us, then yes, we need to deal with it, and we need to understand what might happen, but it's not really our problem anymore, right? But if it is due to us, then we actually need to start thinking about how to prevent worse change. And so let's take a look at why our climate is changing. So here we have our 7 reasons that climates can change, and I want you to tell me which 2 of those can we really pretty much ignore if we're just looking at how climate has changed over the last 100 years. So take a look at my list. Which ones of those do you think we can ignore? I would agree with the 76% or so that I reckon we can pretty safely ignore the continents, mountains, and oceans zooming around the world. They're not going to do that on 100-year timescales, okay? And people have asked me about that. This happens on much longer timescales, millions and millions of years, okay? You look at, say, a good example is how fast North America is moving away from Europe, okay? It's moving away at about the rate that your fingernails grow, okay? And so if you didn't cut your fingernails for a year, it would be really disgusting, but that's how far North America would have moved away from Europe in that time. So it's a really pretty slow process, okay? We're not going to need to think about that in terms of the last 100 years. Also changes in Earth's orbit, okay? So remember that our shortest Milankovitch cycle, what's the name of the shortest Milankovitch cycle? Begins with a P. Precession, absolutely. And how long is it? Can you remember? 20,000 years. Absolutely. And so if we're just looking at the last 100 years, it's not going to make a huge difference, okay? If anything, what should have happened over the last 100 years is a tiny, tiny decline, okay, in the amount of incoming solar radiation in northern latitudes, okay? And a couple of people asked me, are we headed for a next ice age at some point? And you know, that's a really good question. If we hadn't messed with the composition of the atmosphere, if it was just where it was before at 300 ppm or so of carbon dioxide, then absolutely, as the Milankovitch cycles reorganize themselves, in a few hundred years, in a few thousand years, we would be heading into another ice age, and we'd be undergoing global cooling. And the really big question is that now going to happen? Have we messed with the atmosphere enough that we actually wouldn't go back into these sort of cycles that we've been seeing happen for at least the last 2-3 million years? And so that's a really interesting question, and I'm afraid I don't have a good answer for you just yet. A lot will depend on what we do in the next 100 years as to whether that might happen or not. But it's certainly not something that's going to happen in the next few hundred years at least. Okay. But we really need to start thinking about all of these other things. All of these other things are possible reasons why we might see changes in our climate. But the nice thing is, when we think about the last 100 years, is that we really have reasonably good observations of a lot of these things for the last 100 years. We can really start to pin down more carefully which of these might be responsible. Okay? And one of the ways that we do that is we have our climate models. We'll talk in more detail about this on Thursday, but we have models, we have computer models that incorporate all of those different parts of the climate system that you saw on that first diagram. So it includes the atmosphere, the biosphere, the oceans, ice on land and in the ocean. And as you change one thing, we have the physics written in sort of equation form that means as you change one thing, that has an impact on everything around it. Okay? And it's definitely not perfect, but it's actually a remarkably good sort of representation of the climate system so far, and we're still working on those. But this is what happens if we run those climate models for the last 100 years with what we know about those different forcings, with what we know about what the solar variability has been, with what we know about how the surface has been changing in terms of albedo and the type of biosphere, in terms of when the volcanic eruptions were, like that big Mount Pinatubo eruption that I showed you in that photo at the very beginning. Okay? And if we run our models with just the natural forcings, we take out all of the human-caused influences, then what we get are those blue areas on my graph. Okay? So on my graphs in various places, you can see the black line here represents the change in temperature through time. Okay, so that's what my black line is, and here you've got the global. This is what it is over land. You can see there's more of that temperature change. This is what it is over the oceans. And so the blue shaded area is what happens when we run our models lots of times with just the natural forcings, things like solar variability, volcanic eruptions. And then the pink area is what happens when we run our models and include both the natural and what humans have been doing, for example, changing greenhouse gas concentrations, changing the albedo, changing the surface. And you can see that really up until maybe 1970, 1980, it was quite difficult to tell those apart. It was much more difficult to say that, for example, solar variability wasn't driving a lot of the climate signal that we saw, and it probably was driving more of the climate signal that we saw. But really, in the last 20, 30, 40 years, we've seen that difference between the natural sort of models and the models including human influences is really widening. It's widening fast, and that makes it much easier for us to work out what of an influence we are having. Okay? And so really, it is down to us. There's no way around this. And what we can do is we can look at each of those different factors that goes into our models, and we can work out how important they are. And we can work out from fairly fundamental physics in a lot of cases, for example, the greenhouse gases, how much warming they would cause. Okay? So this is a really cool graph. It shows the different things that could cause warming and cooling of our climate system. So any sort of bar above 0 means that it's causing a warming. Anything below means that it's causing a cooling. Okay? And then down here, this is pretty important, level of scientific understanding. Okay? So we go from high for greenhouse gases all the way down to very low for solar. Okay? We don't really understand why the sun changes the way it does, and we're less clear on sort of how it controls our climate, okay? And so we have this sort of full range of things in the middle, and this column shows basically how much extra warming you would have. So if we add up all of our greenhouse gases, things like our carbon dioxide, methane, nitrous oxide, halocarbons, then they would contribute about 2.5 watts per meter squared. So do you remember way back now, we were talking about the solar constant and things like albedo, and we were working in watts per meter squared. So this is the effect of adding those greenhouse gases. We are changing that energy by 2.5 watts per meter squared. And that doesn't sound like a lot, and it isn't. Where is it? It's about a Christmas tree light's worth, okay? So if you imagine that what we've done effectively with adding greenhouse gases right now is we've added as much energy as you would add if you put a Christmas tree light on every single meter squared of the Earth's surface. And that's not a lot, but they give out a certain amount of heat, right? If you sort of touch them, then they feel warm. That's how much warming is happening every second of every day over each meter squared of the Earth's surface. So it's not inconsiderable. Okay, so I have a question for you, which is, of those drivers, of those things that affect climate, which of them has the greatest uncertainty associated with them, okay? Which of them has the biggest error bars? Is it carbon dioxide concentrations, the solar, albedo, or aerosols, okay? So let's go back and have a look at that. So which has the biggest error bars associated with it? So have a look, and then I'll flick back to the options. Okay, any last answers for me? Okay, let's take a look. So we seem to have a little bit of disagreement, okay? So if we look back, which has the biggest error bars? What are the error bars? What are you looking at when I ask for looking at error bars? The black lines, that would be a good start. Okay, great. So if we're looking at error bars, we're looking at the black lines. Okay, so if I look at the greenhouse gas concentrations, then what this little bar up here means that, okay, this is what we think it is, but it could be anything up to here or down to here. Okay, that's our error bar. Okay, so which is our biggest error bar on here? Aerosols, thank you, absolutely. Aerosols, we know that they cool, but we have absolutely no idea how much by, okay? And we also see all of these different aerosols. We really have a huge amount of uncertainty there, okay? And solar, we may not understand it very well, but we don't have as much uncertainty as we do with aerosols. Okay, this is a horrible graph, okay? This is the latest IPCC version of that old one. And I don't like it anymore because it's really not very simple to look at, right? It looks terrifying. And it's basically showing you exactly the same thing as it was before, but just a little bit updated with a little bit more information on there. So it shows you things like CO2, methane, nitrogen gases. It shows you aerosols. Again, we're still pretty uncertain. It changes due to land use, changes due to solar irradiance. And I want you to look at the way they've described these. If you look, all of these top ones here, basically everything other than changes in solar irradiance, these are all anthropogenic. These are all human factors. This is the only natural factor on here, okay? But what I do like about this new version is this little part down here, okay? So this basically adds up, takes away this, and sort of also does that for the error bars to get a total change. What's the total change of all of these different things? And it also does that through time. So for 1950, you can see that the amount of warming that we were experiencing per meter squared of the Earth was maybe 0.6 watts, 0.6 watts, and our uncertainty was sort of lower. As we moved to 1980, we had maybe 1.2 watts per meter squared for every sort of part of the Earth. And then in 2011, we're seeing more like 2.3, 2.2, okay? So you can see that through time, we're adding extra amounts of energy as we move forwards. Because that amount of CO2 in the atmosphere is building up and building up, then the amount of energy that we trap each year is building up and building up, okay? And so we're getting warmer each time. Okay, so, bother, I was going to ask you this question, but I got ahead of myself. So why, right? So we're saying that if we go back, we can see that really the main thing on this graph are the greenhouse gases. And if we look at the particular greenhouse gases, really the main one is carbon dioxide. Methane has been a big contributor, but really in the past sort of decades, it's been leveling out. And that's really good news for us. Whereas CO2 potentially could just keep increasing. And so really I'm going to focus on carbon dioxide for the rest of today, because that's really the main driver of the warming that we're seeing. And so I was going to ask you, why do we have lots more CO2 than we had before? Okay, and it's because of this. Because we have so many people, okay? If we want to look at most environmental issues, the really fundamental bottom line is that the rapid population growth that we've experienced, plus the enormous sort of resource consumption per person, and that's increasing as well through time, is really having a huge influence on the planet. What we could do pretty easily if there were maybe 1 million of us, we can't necessarily do if there are sort of 7, 8, 9 billion of us. And so I want you to think about when your parents were born. When were they born? 1960s, maybe 70s? Okay. Mine were born in the 50s. There were 2.5 billion people on Earth in 1950. Now there are 7 billion people. Isn't that astounding? There's a little clock, I'll post it on the Facebook page, and you can work out of that sort of 7 billion what number you were, okay? I was something like 4.6 or something. And so just in my lifetime, 2.5 billion extra people on the planet, okay? That's an enormous change, a huge change. And so if we want to sort of divide the resources of the world, remember we're a closed system, we're not going to find magic extra resources, then that we're dividing it between more and more people, okay? And increased technology and increased energy demand is really putting a strain on the planet, okay? And so my little question to pose to you, so what I ask in my ESS 1 class is there an upper limit of population on Earth? Is there an upper limit to how many people the Earth could hold? Yes? No? What might limit the population on Earth? What can't you live without? Water. Water's a good one, okay? What also can't you live without? Food. That was also another good one, okay? We're going to struggle to feed 9 billion people by 2050, okay? So these are things that I think are really fascinating questions, and we're going to come back and talk more about population and how it might increase on Thursday as well. But it's really the bottom line. That's why we have so much extra CO2 in the atmosphere, because we have a lot more people, the number of people is still increasing, and they have sort of resource demands. Okay, so as a reminder, we haven't thought about it for a while, but this is our carbon cycle. This is the idea that just like the hydrologic cycle, there's only so much carbon on Earth, but it moves around between different reservoirs, okay? And so what we're doing by extracting it from fossil fuels and burning it, and also changing the amount in our biosphere, we're putting some of that into the atmosphere, but it doesn't necessarily just stay in the atmosphere. It will also sort of carry on going through the cycle. And so because we've got more in the atmosphere, more of it dissolves in the ocean. We've talked about the consequences of that for the acidity of the ocean. Also, it's easier for life to grow because there's more CO2 there, and so there's a certain amount of that. But you can see that really the only process that removes carbon from our surface of the Earth is really this one. We really, to get carbon out of this system, out of the atmosphere, ocean, life system into the geosphere, we have to form sediments, and that's a really slow process. And so a couple of people said, if we stopped emitting CO2 tomorrow, could we just go back to normal? Well, yes, but it would take thousands, tens of thousands, hundreds of thousands of years potentially for that carbon dioxide levels to drop back to where it was before, unless we come up with clever technologies that could help us with that. And that's not out of the question. So what did we do to the carbon cycle? So there are two main culprits for why there's this extra carbon in the atmosphere. The first is deforestation. And I was really fascinated when I found these little maps. These maps show you the area of the US that used to be forested in 1620 and the amount that was forested in 1920. Isn't that amazing? That's really quite astounding at how much forest was lost in the US. Same thing happened in Europe just a few hundred years before. Most of the UK used to be covered in forest, and that was lost. And that's happening worldwide now. It's happening in the tropical forests much more than in the US and elsewhere. But certainly if we add up, we can get pretty good estimates of how much we've added, and it's probably about 200 gigatons of carbon to the atmosphere since 1850 or so. Okay? And that's still about 0.5 to 2 gigatons of carbon right now. But if we look at fossil fuel burning, then we've added 280 gigatons to the atmosphere since 1900. And if you look at how much is going in per year, that is what is going up every year. And so now we're adding 6 to 7 gigatons, so billion tons of carbon to the atmosphere each year. Okay? And someone asked me a very good question, okay, which is, how do we know it's us? So we're going to talk about that in a second. But I wanted to make the point here. This is sort of what happened to that carbon dioxide that we put in the atmosphere between 2003 and 2012. About half of what that extra that we put into the atmosphere went into the oceans. The oceans have really been helping us out by taking up not just energy to avoid us warming more quickly, but also carbon to avoid that, more of that carbon building up in the atmosphere. Also, we've been growing more. In some places in the US, we're getting reforestation, perhaps on the East Coast in some places. But also those plants might be growing better because there's more CO2. So certainly some of that has gone back into sort of biosphere on land. Okay? And then the leftover is actually what is building up in our atmosphere. That's what we see on that curve that steadily rises. But we can't necessarily guarantee that that is going to continue to happen. We can only grow plants over so much of the land surface, and eventually they become limited by other things. What limits water? I just told you, not doing very well today. But water can limit plant growth, right? And so just because we put more and more CO2 in the atmosphere doesn't mean that they might not be limited at a certain point by water, for example, or nutrients. Also, what happens to your soda as it warms up? It goes flat, right? And it's the same thing. As we warm up the ocean, we can dissolve less and less carbon dioxide within it. And so we can't necessarily rely on the oceans and life on Earth to keep on absorbing as much of that extra CO2 as it has been doing. So that's a concern. So I don't mean to scare you, but I think this is something that's really cool. It's not something, hopefully, that you'll have heard before unless you were in ESS 1 with me, or unless you're going to take it next quarter. And I was delighted to see a few people are. A lot of people say, well, how do we know that that extra CO2 is us? How do we know that it's not volcanoes? Well, first of all, we can just add up how much we've burned and how much forest has been lost. But it's a reasonable question, okay, given it's difficult to quantify, perhaps, how much CO2 is coming out from volcanoes worldwide. And there's a couple of really neat ways that we can see that it is due to burning and that it's due to us burning fossil fuels in particular. And the first is, if we're burning something, it uses up oxygen. And so if we're burning fossil fuels, then we're also going to use up oxygen in the atmosphere. And we can actually see that. And I think that's really, really fun. So fun in terms of really amazingly scientific evidence rather than good. But the main thing is we are not going to die out because we're going to lose all our oxygen. This is a tiny change. Remember, oxygen makes up 20% of our atmosphere right now. It's a huge, huge component. This is a very small change, but it is a measurable change. okay? The same time as CO2 goes up, the oxygen goes down, okay? You can also see little wiggles on there. What are those little wiggles representing? Seasons, absolutely. Photosynthesis. So just like the Keeling curve showed that change in CO2 because of photosynthesis, this is also showing that change because of photosynthesis, okay? So if we look at our atmospheric oxygen levels, they're maybe about 0.1% lower than they were before we started burning fossil fuels. And then this is the slightly scary bit, but it's completely manageable, so don't panic, okay? And this is carbon isotopes, and I included this because this is some of the work that I do. I look at carbon isotopes. So has anyone heard of an isotope? Some people have, I know. Okay. So isotopes are, you take an element like carbon, like oxygen, but you get slightly different weights because they have slightly different numbers of neutrons in their nucleus. So it doesn't affect the chemistry, it doesn't affect the sort of reactions that they carry out or anything else, but because one is heavier than the other, then it does sometimes change the sort of the ratios that you see. So in particular, in our on Earth, we have 3 different isotopes of carbon. So we have 3 different versions of carbon, basically. They still all behave like carbon, but they're slightly different weights, okay? So we have carbon-12, we have carbon-13, and we have carbon-14. And carbon-14 is particularly interesting because it's created really high in the atmosphere by the interaction of cosmic rays with nitrogen, okay? And then that radiocarbon, once it's formed, it's radioactive. So over time, it decays away. So after 50,000 years or so, any sort of radiocarbon, any 14 carbon that was in your sort of thing to begin with is gone, okay? So let's look at a couple of examples of this. So if we look at our tree, okay, it's made up of a lot of 12 carbon, okay? So let's think about why that is. If I ask you to lift up something very, very heavy or something very, very light, which would you probably prefer to pick up? The light thing, okay? And it's the same thing with life. Life is pretty lazy. It doesn't want to use the really heavy thing. It takes more energy to do that. And so if you're a tree, you prefer that 12 carbon. It's lighter. It's easier for you to use it in chemical reactions. Does that make sense? Yeah? Okay. So if we look at our tree compared to a volcano, the volcano doesn't care, okay? It doesn't care whether it's 12 carbon or 13 carbon, okay? But the tree does. So in our tree, we have much more 12 carbon. We have very low amounts of 13 carbon. In our volcano, we have higher amounts of 13 carbon compared to our 12 carbon. Does that make sense? Yes? Okay. So now let's think about this 14 carbon. This 14 carbon's created high in the atmosphere, okay? And because it's in our atmosphere, it also gets incorporated in some way into you. You have some radiocarbon, into trees, anything that is taking carbon from the atmosphere, okay? And so our tree contains a certain amount of carbon-14. Our volcano, where is that carbon dioxide coming from? It's coming from the middle of the Earth, right? Okay? So that carbon isn't coming from the atmosphere in any way. It's coming from the middle of the Earth. And so it's not going to have any 14 carbon in it. Does that make sense? Yes? Okay. So I have a challenge for you. I always like a challenge, right? So now let's think about what would the ratios be in fossil fuels. So if I take fossil fuels from the ground, so coal and oil, okay? So remember, they're fossil fuels. They're formed from the remains of dead plants and animals, okay? But they're millions and millions and millions of years old. So what sort of types of isotope ratios would we see in carbon dioxide from fossil fuels, okay? So think about it for a minute. Consult with your neighbor, consult with your TAs. Wave at me, TAs. 1, 2, 3, okay? So what do you think? Okay. And this is a mean question, by the way. I do understand that. Please don't pack up just yet. I do have another iClicker question for those of you packing away. Okay. So let's take a look and see what we think. Okay. So let's work through this together. Okay. This is a fossil fuel, right? So it's made of the remains of plants and trees and animals. Okay. So is it going to have high amounts of 13 carbon or low amounts of 13 carbon? Low. It's going to be just like our tree, right? There's going to be lots of 12 compared to 13. Okay? When did those form? Are they brand new? Did they grow yesterday, or did they grow millions and millions and millions of years ago? Millions and millions and millions of years ago. So is that anywhere within the last 50,000 years? No. So they would at the time have had 14 carbon in them when they were growing. But after they died, they weren't taking in carbon from the atmosphere anymore. And so whatever 14 carbon there was would have decayed away through time. And after 50,000 years, there wasn't any of that left. Okay? So if you put C, you were right. Okay? So there would have been low, I've got two more things to say, okay? So this would have had low 13 carbon and no carbon 14. And so if we're putting that carbon into the atmosphere, we should be able to see that same change, right? And that's what we do. Please don't talk for this last 2 minutes, okay? So this is what we can see. If we measure the ratio of carbon 13 to carbon 12, we're seeing that it's getting lower. We're putting more 12 into the atmosphere compared to 13. It has to be coming from something that was living. So you can see that through time, that ratio has been falling, which is really neat. It's what we predict, okay? Not only that, but if we look at, say, tree rings and the carbon 14, we can see that the carbon 14 of the atmosphere was also dropping because we were putting these fossil fuels back in. Unfortunately, we then messed it up completely in the 1950s because we set off lots of nuclear bombs. And nuclear bombs also made lots of carbon-14. And so we couldn't then measure it anymore in a very unhelpful way. But you can see that before then, we were starting to see this big drop. And that was because we were putting this old carbon in there. Okay? So it's always a dangerous question. But do you think that human activities are the main reason that Earth's climate is changing? Okay, so let's take a look. Still the same as before. I never change people's opinions with this. Okay, so I have some main points that I want people to take away from today. Our climate is changing, and it's changing very rapidly. That is not something that there really is any discussion about. There are many factors that control climate, but the main reason for that change is increased greenhouse gases. There is really also not much debate about that. The reason for those increased greenhouse gases is because we have seen an enormous increase in our population and a corresponding increase in demand for energy and resources. And the carbon dioxide levels in our atmosphere are nothing to do with the natural system. It really is us that's changing that. And that, again, is not something that we can argue. There are certain things that you can have an opinion about. This is as scientific a sort of question as any other I've asked in this class, and the answer is yes. Okay? Great. I will see you on Thursday.